just assume that there is a quantum gravity scale, then obtains a big fine-tuning, and then the two questions are related: why gravity is so weak compared to the other interactions. Yeah. So the standard pixel to address some of these questions is the so-called supersymmetry, low energy supersymmetry. Supersymmetry is a new symmetry that postulates that every known particle has a partner, which is called superpartner, which has a spin differed by half. This symmetry implies the cancellation of the large quantum corrections to the Higgs mass. And in order this to happen, the superpartner masses should not be far away from the weak scale, otherwise this fine-tuning problem that I described before will come back. There are several advantages of this low energy supersymmetry. Low energy is called because the superpartners have masses near the weak scale, so within the LHC grids. One advantage is that it predicts naturally elementary scalars. The reason is that this asymmetry between bosons and fermions. So once we have fermions, there should be also scalars. We know now that scalars exist. Until now, all scalars that we knew were composite, like the pions. And it is once we found one scalar, it is very natural that we should find later on other. And we know that in other domains, like inflation, for instance, postulates and also a scalar which is an inflaton that could be also there. So supersymmetry predicts naturally elementary scalars. Then also it allows to have this unification of forces. And going back to this scheme, here I cheated a bit. The reason is that if you see these curves have been bent, and the reason that of this bending is that I postulated here, I assume that there is supersymmetry at this scale, at the TV scale. So all the superpartners contribute to the evolution of the forces. Without assuming supersymmetry, this unification of couplings will not work in an exact way. It will be approximate, but it will not work. The supersymmetry allows you to make it exact. Then it also provides a natural candidate for dark matter, which is the lightest supersymmetric particle. In most supersymmetric theories, the lightest supersymmetric particle is stable. It comes together with the reason is that there is a discrete symmetry which protects its decay, which is called asymmetry. And this has the right properties of the dark matter. It also predicts the mass of the Higgs and predicts, not in an exact way, but a bound for the mass of the Higgs, which is less than about 130 GeV. So therefore, the value that we found, that LHC found, 126, is within this bound, and therefore it is compatible with supersymmetry. And finally, supersymmetry predicts a rich spectrum of new particles within the reach of LHC that could be studied for the next round. On the other hand, there are also some problems. One problem in supersymmetry is that it introduces new parameters, which are many parameters, because these parameters, if you want, are the masses of all the superpartners, of all the particles, superpartners of the known particles. They are called soft breaking terms. The reason for all these parameters is that we don't know exactly how supersymmetry is broken. If it is not broken, then the superparticles should have the same masses as the known particles, and this is we know that it's not true because supersymmetry is not has not been discovered yet, and we don't know if it is there. So this is one of the theoretical problems of supersymmetry. Another is that the standard model has some global symmetries which are not automatic in supersymmetric theories, such as the baryon and lepton numbers, which guarantee, for instance, stability of the proton that does not decay, or that guarantees that there are no processes that change the flavor, which is the type of flavor is the type of quark family for quarks that has not been seen. So there should be conditions to guarantee that there are no that these symmetries are still approximate there. Also, there is no satisfactory model of supersymmetric unification. In other words, if one wants to put them to build up a model that realizes the unification of forces together with supersymmetry, then there is no mathematical satisfactory model for the moment. Another problem is the so-called mass of the Higgsino. The Higgsino is the fermion which is the partner of the Higgs. This particle should have a mass. This mass is supersymmetric. However, it must be of the same order as the masses of the other particles that break supersymmetry. And one doesn't know the reason why that should be of the same order. And finally, perhaps the most important question right now, the most important problem right now comes from the fact that supersymmetry has not been seen, and therefore there are bounds which are quite important now for the masses of the superpartners, and these bounds are quite heavy, and they bring back part of the fine-tuning problem, not to many decimal places, but perhaps 2 decimal places, which make some people worry about the whole motivation of the hierarchy problem, if you want, the supersymmetry. So these are, of course, theoretical issues, but just to give you an idea of why we start worrying about whether this. There are some pros, some advantages, but also there are some problems with supersymmetry. Now, on the other hand, of course, supersymmetry does not address the question of quantization of gravity. There is another theory that addresses this question, which is called string theory. So string theory is a mathematical framework that unifies quantum mechanics with general relativity. And the main hypothesis is that it replaces the notion of point particle as a building block of matter, of physics, by extended objects, which are strings, which can be either closed or open. And in this theory, the particles are coincide with string vibrations. So you can imagine classically that you can have an open string or a closed string, and these are various modes of vibration. In quantum theory, these modes of vibrations correspond to particles, and that's how the particles arise. So it turns out that this theory, as I said here, contains a massless particle which has spin 2, so it contains gravity in as a quantum theory, and it also provides a framework for unification of all other interactions, because in addition to gravity contains also other spin one particle that can that would accommodate the other forces. And finally, it's a very nice mathematical theory, because in particular it does not have what is called the short distance singularities or ultraviolet divergences that field theories have. So this is a set. These are the main reasons why this theory has been studied a lot over last decades. The main parameter is either a mass scale, which is I would call mass of the string, or a size, which is the size of the string. So the rigid string describes the known particles, so the massless particles on the spectrum are those of the standard model plus the graviton, while the vibrations give rise to an infinite number of massive particles. So the question, of course, is that if string theory is realized in nature, it is a theory of quantum gravity, then at what energies they should be observed? At what is there a possibility to make? Are there low energy string predictions, for instance, at the LHC? Now, the answer to this question can vary, and it depends mainly on what is the value of this parameter, which is a string scale, or the value of the string length. Traditionally, when the string theory was introduced, it was believed until approximately 94 that the string scale should be near the Planck scale. String theory is a theory of quantum gravity, and therefore the string length is very small, 10 to the minus 32 centimeters. And if that is the case, of course, it is difficult to imagine how it can be tested in accelerators. Of course, it could be tested in other ways, if there is a way to test quantum gravity, perhaps with early cosmology, but not in particle accelerator. However, after 94, it was realized actually that the string scale does not need to be tied to the Planck scale. It can be its own independent parameter of the theory. It could be decoupled from the Planck scale, and can be therefore anywhere between the Planck scale and low energies, let's say at the TV, where there are experimental bounds. So if the string scale is high, then the string theory provides a natural framework for unification and supersymmetry. But as I said, there is no string test at the LHC. However, there is another interesting possibility, that the string scale is at low energies, is near the electroweak scale. And in this case, it can be used as an alternative to supersymmetry in order to address the hierarchy problem that I described, because the string scale precisely replaces the scale of new physics. So if the string scale is, let's have set here. If lambda, the scale of new physics, is a TV scale, then there are no anymore larger quantum corrections to the Higgs mass. What I will describe in the next is how this can happen and what are the experimental consequences of such a possibility that could be tested at the LHC. So actually there are two main predictions of string theory. One is extra dimensions, and the other is the possibility of what is called brain worlds. So what about extra dimensions is that the consistency, the mathematical consistency of this theory implies that space does not have just 3 dimensions, it has extra dimensions. There are extra new dimensions of space, 6 in the most standard theory. And that is, of course, new, completely radical concept. And the second ingredient, the second prediction, is that the matter and our engaged forces, therefore our universe, could be localized in less than this 9 dimensions. It could be the one that we see. So it would give a picture that our universe would be just a kind of extended membrane that is floating in the space of extra dimensions. So let me elaborate a bit in these two concepts. So the first is the concept of extra dimensions. The first question that we would ask is if there are extra dimensions of space, then how they escape our observation. Actually, extra dimensions were first introduced by Colloquia and Klein back in 1920. In there, they were trying at that time to unify the two known forces, which were gravity and electromagnetism. And they went to a five-dimensional theory. So the answer they provided is that indeed there could be extra dimensions of space, and if these extra dimensions have a finite size, then it would be unobservable if the size is sufficiently small. Why? Because if they have finite size, then it costs energy to send a signal along this extra dimension. And the minimum quantum of energy that one needs to send is called compactification scale. It's the inverse of their size. And just from this one can find experimental limits on their size. So just to visualize, suppose that our universe is along this line, and there is an extra dimension which corresponds to a small cycle. So every point of space there is a small cycle. If we are far away, then we don't see this extra cycle. We see just the line. But if we start approaching, as you approach, you start realizing that there is an extra dimension which has which is a small cycle to every point. Now, this can be generalized to more than one dimension. For instance, you can have two dimensions which correspond to two different cycles of different sizes, one smaller and one bigger. So as you approach the point, let's say you start realizing that there is one dimension that has that corresponds to one cycle. You approach further, you realize that there is a second dimension, and so on. So this approach, if the size that we're talking here are very small sizes, the sizes that are probed in accelerators, this probing to see the extra dimensions is by doing high energy experiments and collision, for instance, quantum high energy. So the experimental limits on their size is that the size should be less than any size that is probed in high energy experiments, which are roughly, let's say, around 1 TeV, and therefore this corresponds to size less than 10 to the minus 16 centimeters. So if there are extra dimensions of size smaller than 10 to the minus 16 centimeters, then they are unobservable, and there could be there, simply we have not detected them. So there is, the second question is, suppose that there is such an extra dimension, and suppose that its size, let's say, is near the size which is probed by LHC, how will we detect its existence? The answer was provided again by Colloquia and Klein, and the observation is that the motion, so a particle that it moves in the internal space, in the extra dimension, give rise, from our point of view, to a mass spectrum in 3 dimensions. So a mass spectrum which is called Colloquia-Klein spectrum. And the reason is the following. So suppose that you have one extra dimension which is a circle, as before. To this extra dimension, there correspond plane waves, exactly as the plane waves in the other dimensions. And these plane waves have an extra coordinate, y, and the corresponding momentum p. This extra coordinate is periodic because it forms a circle. And therefore, this implies that these momenta are quantized in the same way that you have quantization of momenta, for instance, in a box, when phenomena in a box. So this quantization of momenta is in units, integer in units of the inverse size. One sees that if I write from the three-dimensional point of view, if we start with a massless particle in 5 dimensions, let's say, and you move the fifth component of the momentum on the other side, then it gives rise to a mass spectrum in our space with masses 0, 1 over r, 2 over r, and so on. So the zero mode corresponds to the let's say to the photon, while the other particles 1 over r, 2 over r, and so on, they correspond to massive photons, which have the same property of the photons as the photon, but it's a mass. They have a mass. The way to probe these extra dimensions is by producing these Colloquia particles, which are called, in other words, the spectrum of massive, for instance, photons, if we talk about the photon. In the limit where the energy is large compared to the compactification scale, which is this 1 over r, then one can emit, one can produce too many massive photons, and one can think that this additional component of the momentum becomes quasi-continuum, and therefore it is like it gives rise, like you have an extra dimension, and like the photon propagates in one extra dimension. So it gives back the propagation for the internal space. So this is about extra dimensions. What about the possibility of brane work? So this concept is that one could imagine a framework in which there are extra dimensions. However, our universe could live in a membrane which is fixed and which is floating in this space of extra dimensions. In other words, suppose that as the forces that we exhibit are confined in our universe is confined in this membrane, which is transverse to extra dimensions in space. In other words, this implies that there are two types of extra dimensions, two types of dimensions in general. Dimensions along the brane and dimensions transverse to the brane. Those that are along the brane are dimensions that we can probe by the photon, by the light signal, and by other interactions, while those that are transverse to the membrane, we cannot probe them by the standard model interactions, but they could interact with us gravitationally. And the reason is that gravity sees energy, and if there are extra dimensions, there should gravity should be possible to we could send gravitational signal in these extra dimensions. So previously, what I said, I mentioned the limits of extra dimensions along the membrane. So if the space along the membrane does not include only our 6 dimensions that we observe, but extra dimensions, these dimensions should have a size which is less than 10 to the minus 16 centimeters. However, if there are extra dimensions which interact with us only gravitationally, we cannot send a light signal, then obviously the bounds and the limits of the size of these extra dimensions would be different. And the reason is that Newton's law and gravity does not have been tested at short distances in the same way and the same precision as the other interactions. And actually, the limits on these gravitational type extra dimensions are about 1 millimeter. So these extra dimensions would be quite microscopic, 1 millimeter, and still they could be unobservable simply because we have no way to communicate with them, along them other way apart gravity. So this idea has given, this possibility has given rise to experiments, various experiments to be performed all over the world, which test gravity at short distances. And this bound comes from the Ignatios experiment in the States, which probed Newton's law at down to 50 micrometers, and therefore, if there are extra dimensions which interacted of us only gravitationally, the size of these extra dimensions should be less than about 50 micrometers. And it is just a curiosity here that this size corresponds to a size that one can find from the dark energy. If we translate the dark energy density to a length scale, then we find the length scale which is comparable. For the moment, of course, there has been no deviation from the Newton's law, and which gives this balance. So and then the main point concerning the hierarchy is that if there are extra dimensions of which are transverse of the type of gravitational type, then if these extra dimensions are sufficiently large, one could explain the apparent weakness of gravity compared to the other forces. Why? Because one could imagine that the total force of gravity is much bigger than the observed force, simply because there are extra dimensions, and the gravitational field could be spread into the extra dimensions, and makes gravity to look weak to us, although in reality it has the same force as the other interactions, the same strength as the other interactions. So this is what this formula says, that the total force is the observed force times the volume of the extra dimensions. So this total force is measured by the Newton's constant in extra dimensions. The observed force is the Newton constant in 4 dimensions, and the volume is determined by the size of the extra dimensions. So if one assumes that there are a certain number n of extra gravitational dimensions of size r, and we impose that the force of gravity is comparable to the force of the other interactions at the TV scale, so it's order 1 at the TV, then one finds that the size, one can compute using this formula the size of the required size of the extra dimensions, and this size, of course, varies a lot depending how many there are. So if you have one extra dimension, then the size that one finds is 10 to the 8 kilometers, so this is obviously excluded because we have not seen. However, if one has from 2 up to 6, which are the possibilities in string theory, then one finds that the size which is required for the extra dimensions varies between a fraction of a millimeter to about a Fermi. So all these possibilities are viable, are possible, compatible with the present observations of testing gravity at some distance. So this is a possibility that allows to address this hierarchy problem and the apparent weakness of gravity at the same time using extra dimensions. So this scenario of extra dimensions precisely can be realized in string theory by combining the extra dimensions of string theory with the brane world, which is called the brane world. So as I mentioned, string theory has 2 types of strings, closed strings and open strings. It turns out that gravity is described by excitations of closed strings, which propagate in all dimensions of string theory, so 10 dimensions if we include the time, 9 plus 1. While the standard model interactions are described by excitations of open strings, which have ends, and these ends are attached on the brane of the universe, which are called D-branes. And so this is the picture that can visualize this possibility.